Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. So far we have looked at the theory of four-step travel demand model, then we looked at what kind of database is used to build the models, and now in this section we will look at how the four-step travel demand model goes from theory to practically going in the actual MPO travel demand models. So let's get into it. So the first we are looking at implementation of four-step travel demand model, is also called model development, given the large data size of travel demand model. So the first aspect of travel demand model, or let's call it zeroth aspect, is the large data set. Let me explain. Uh, the input to travel demand model comes from two important files. One is TAZ file, another is roadway file, roadway and transit, like we uh, saw in previous video. So within TNC files, we saw that there are a lot of zones. Let's say typically, let's say 3000 zones, and there are a lot of attributes for each TAZs. So let's say household size, employment, number of households, population, and there are many other attributes, and these attributes are repeated for existing year, and then repeated for interim year, and then repeated for the future year, because the household size and all the information might change between years. So it creates a lot of data points. Let's say there are 50 columns, so when we multiply them together, it will be 150,000. So we have 150,000 data points to fill up for the TAZ layer itself. Now for the roadway, the number of links are even much greater. So number of links for roadway, let's say for simplicity, 30,000. And similar to TAZs, they have a lot of attribute for each years, and usually is greater than 50, but for simplicity, let's say there are 50 different attributes combining existing, interim and future years. So we have 1.5 million data points to fill up as input. So we are looking at 1.5 million data points to fill up as input. So that's why it's called large data set. So given the large data set size in terms of input, so large data set input size, numerous assumptions and approximations are used while developing a regional model. So we cannot go and collect this much amount of data probably very easily. So a lot of assumptions and approximations are made, and we need to be aware of those assumptions and approximations to kind of know that okay, these are the approximation, and if those approximations are valid on a smaller level travel demand model. So the travel demand models are built for bigger MPOs for a bigger region, but when we work on project, we are looking at a smaller region, and we want to make sure those assumptions and approximations holds true for the smaller region we are working on as well. So that's the point number one, which is valid for all the steps we are going to discuss, not only for trip generation. So the first step in four-step travel demand model is trip generation. Now to get trip generation, if we remember our theory, what we need is TAZ attributes or TAZ characteristics. We have TAZ characteristics. Based on the theory we discussed, we will use the TAZ characteristics uh, to get to feed it into different regression equation called cross classification regression equation. So we have different curves, and based on the TAZ characteristics, we will see which curve to use, and then we will sum up all the trips generated. So TAZ characteristic will decide which curve to use, then which will calculate total number of trips generated, um, trips generated um, from each TAZ, and then we sum it up. So for each TAZ, we sum it up for all the developments. This is how we discuss the uh, trip generation works in theory. So let's look at how we collect all this data in practice. So the first one is several socioeconomic data for TAZs are obtained from Public Use Microdata Survey or PUMS provided by US Census Bureau. So this is very important. So I have been kind of discussing in the previous video that, let me draw with a different color. So I have discussed that usually the TAZ boundaries are same as census tracts. So this is my TAZ, and usually this is also the census tracts. So one big reason to set the TAZ boundaries same as census tracts is to take the census tract data which is already collected by US Census Bureau and directly call it the TAZ attributes. So the first we take the census tract data which contains information on number of household, population, median income. So one point to note here is median income and not the distribution of income. So we'll talk about that soon. Average household size and not the distribution of average household size, employment and employment type. So census tract kind of gives the average or average information about that census tract, and if we declare it as a TAZ, then we know the socioeconomic data of that TAZ. So that's one of the biggest advantage of declaring TAZ boundaries as the census tract, that we can directly take the census tract data and call it TAZ data. The next step is to use the distribution curve, which is explained here. So a TAZ may contain a household with wide range of socioeconomic characteristics. So let's say we went to census tract and looked at a TAZ, and census tract said uh, the average income is 30,000. So we assigned the 30,000 to TAZ. Now within a TAZ, there are different kind of residents. Some people have higher income, some people have lower income. So a TAZ may have households with different socioeconomic characteristics. So what we do is we take this average number and change them into a distribution based on the distribution curves, which is explained here. In practice, the household size, household income, number of workers in a household are distributed based on distribution curves. These distribution curves are developed using regional PUMS dataset. So there are so this is census data at TAZ level. Then we take the census data at regional level and then come up with the distribution of income. So let's say the this is a curve for uh, number of people. This is a cumulative curve for number of people having certain income. Then this is another curve. This is another curve. One of the example is shown on the next page. And then what we do is we figure out where our this average lies. Let's say 30K lies here, or an equivalent change to this. So in the example we are using the TAZ income, let's say 30,000. Here in the example, let's say is 60,000, and median income is 55,000, which is regional. So if we take the ratio of TAZ to regional, then we will get 1 point something 1.1, and based on that these graphs, it will lie here. So what we do is we take a vertical curve, a vertical line moving upwards. So the vertical line intersects the blue line here, which correspond to less than 25,000, and it cuts approximately at 45%, 45% mark. Then this dark yellow color or light orange kind of color is for greater than 75, and it kind of cuts here, which is around 24%. Then the red line, which is for 25 to 50,000, is around 21%, and similarly the gray line is around 10%. So what this did is we took the regional curve. There are only one curve typically for entire region for each attribute. So there is one curve for income, one curve for household size, one curve for other attributes, let's say number of workers. So we will have one curve for each attribute, but only one for the entire region. And then based on the TAZ average data, uh, what we can do is uh, we can come up with a distribution. So let's say for another TAZ, the TAZ income is pretty high. So let's say the TAZ to regional ratio is here, let's say 2.1. Then we will draw a vertical line. Well, if I can draw a vertical line with this mouse, then it will cut the top graph here. So greater than 75% will be around 60% of people. It will cut this blue line, which is less than 25%, will cut around, let's say, 25%, and so on. So first, we take the census data, we figure out the average, then we figure out the distribution curves based on the regional data and change that average to a certain distribution. And now we have TAZ, instead of TAZ average, we have TAZ distribution data. Now we use TAZ distribution data using onto the cross classification regression curves. So TAZ distribution data is fed into cross classification regression curves, which we looked into while we were discussing the trip generation. So these are bunch of curves where data is segregated into different blocks and have different curves to it. So this distribution is fed into a set of equations, and based on these equations the total number of trips generated are calculated. So trips generated for each trip purpose, so trip generated for each zone and for each trip purpose is sum of um, all the developments and all the attributes that are playing in the that TAZ attributes. So sum of all the trips generated from all the different kind of developments within the TAZ. So it's kind of, that's how the big process goes. We start with US census data, then assign US census data to TAZ data, but these are average data. Then we use the statewide, let's say statewide curves, distribution curve. So we use statewide. I wish I had a touch pen. It's kind of difficult to write with mouse. Distribution curve. TAZ data using the statewide distribution curve gives us the TAZ distribution for each zone. So TAZ attribute distribution for each TAZ. So TAZ distribution. Once we get the TAZ distribution, we fed it into cross classification regression equations. Those are bunch of equations for different classes of TAZ attributes. Once we feed it into cross classification regression equations, then it gives us total number of trips for that particular zone. So in final, we get trip total for each zone for each trip purpose. We still for each purpose. So we're still calculating for each zone and each purpose at this stage. So this is how trip generation works in practice. I hope it is as clear as it can be. Uh, This is usually kind of still a theory side of things where we are trying to figure out how these are implemented. If we are actively working on travel demand model, then we will be using it. In most of the cases, this process is automated, so we don't actively need this knowledge, but it's good to have this knowledge. Next one is trip balancing, which we talked about when we were discussing the theory. So when we were discussing the theory, I kind of mentioned that there is something called PA table. In PA table, the first row, this is the zone, this is the production, this is the attraction for each trip purpose. For each trip purpose, there is a PA table. So these lists the number of zones. Some of this production is here and some of this attraction is here. And I kind of mentioned earlier that production and attraction barely match in practice. So that's what this is doing. So total number of trip produced and attracted in study area for each trip purpose should be equal. Not only for each trip purpose, but for each period of study. So if we are studying AM period, then the PA table should be balanced. If we are studying PM period, then the PA table should be balanced for PM period. Similarly for night time. However, this is never the case in practice. Never is a strong word, but it's kind of true. We'll probably never see any case where production and attraction are balanced by themselves. So PA matrix for each trip purpose is balanced based on whether production is more important or attraction is more important. So in the example, I think I was giving during theory is, let's say total production is 5,000. Let's say total attraction is 4,500, or the other way around in theory. So if we trust that production is very good, I have full trust in production, then what we will do is we'll scale up the attraction to match the production 5,000 numbers. So we will uh, multiply all the numbers by 5 divided by 4.5 to such that total sum of attractions become 5,000. Now if we have full faith in attraction, then we will scale all the numbers in production equally such that these numbers become 45,000. Now the entire discussion comes about whether to trust production or whether to trust the attraction. So trip balancing has two important components. First one is production and attraction are barely balanced in practice. That's the point number one. Point number two is to balance them, we have to either trust production or we have to trust attraction. We have to trust one of them because both of them are not matching. So we have to adjust at least one. So the second one is, which is important here, is which one to trust. So based on trip purpose, so for home based work, we typically trust the production because we know how many apartments are there, how many residential area are there, so how many trips will be generated. If we are looking at home based work, we trust the production. For every other trip purposes, we trust the attraction. So let's say home based non-work, let's say home based going to school, home based education. So we know how many students will go to school, how many parents or employees will bring their vehicles. So for everything else, we trust the attraction. That's the short story of PA balancing. So if I have to summarize the PA balancing in practice, first production and attractions needs to match, but they hardly match in practice. Then we have to figure out whether we are going to trust production more or attraction more. So for home-based work, we usually trust the production more, and for every other trip purposes, we usually trust the attraction more. That takes care of trip balancing. Now trip distribution. Trip distribution is performed using standard gravity model. If you remember from our theory, a standard gravity model uses a synthesis OD and not a base OD. So it uses a synthesis OD based on impedance function. So it accounts for the future development and future roadway to come up with an impedance or friction matrix, and then friction matrix is translated into particular trip distribution. So this is standard gravity model. The these steps involve the calibration of impedance factor, figuring out what impedance factor or functions to use, and the K factor like we discussed in theory. So an iterative process is used before, I think the model is kind of, this is not an iterative process during the TDM model run. This is during the model development itself. So we are trying to match the TDM OD matrix output to the field collected OD matrix output. So by adjusting these two numbers, we'll try to figure out what is the OD pattern we are getting from TDM, and what is the OD pattern we are getting from the field, and we're trying to match them. So that's the trip distribution calibration, we can call it. And this is done by agencies. This is not a travel demand model calibration. This is a model development when the model is actually being built, even before being used. So this is trip distribution calibration. Next one is mode choice. So we briefly looked at the mode choice in theory, and we looked at multinomial logic regression for the mode choice, where the probability of choosing a mode is directly related to the utility or perceived utility provided by that mode. So in practice, there are three main steps to implementing mode choice. The first step is mode travel times. So there are some concepts that are starting to kick in regarding travel demand model. So I will spend some time on this one, even though it's not kind of that significant, but there are some words I can see which I need to explain in detail, like .NET file, what is highway skimming, and other attributes. So not only related to mode choice, let's look at some terms that are coming from Transcad. So first one is roadway attribute files is called .NET file. So it's also called highway skimming. So if we have a roadway network, and in order to use this roadway network and with current flow, so we have roadway network, but the flow and travel time of this roadway network still needs to be determined. So based on the current equilibrium flow, what we can do is uh, we can extract this roadway network uh, based on the current flow and current travel time. So this process of extracting some part of the roadway network with some attribute is called highway skimming. In highway skimming, we are taking this roadway network. So first we are taking the link node structure. Uh, first, the first thing that we are taking out is link node structure. Then for each link, we are taking out the attributes. Let's say free flow travel time, which is T naught. Let's say alpha, beta, a current travel time, a roadway capacity, anything that influences the travel time. So we extract out this information out of Transcad, and this process is called highway skimming. And when we skim the network, and the file is stored in .NET file. This .NET file also has the routes associated with different origin and destinations. So .NET file is kind of generated by running assignments, and then uh, this also contains route between OD pairs. So roadway attributes affecting the mode choices are extracted in .NET files, commonly referred to as highway skimming. Highway attributes include travel time, travel cost, travel distance. And then similar to highway skimming, there is called transit skimming. Transit attributes affecting mode choice are extracted in .tnw file format, commonly referred to as transit skimming. The transit attributes include transit travel times, wait times, cost, number of transfer, etc. Next step of the mode choice is market segmentation. So first what we did is we extracted out the travel time files. Then the second one is we figure out which segment of market will actually use certain modes. Let's say we are looking at transit. So from experience, we kind of know that transit is mostly used by students or by low income families or low income households. So transit is mostly used by students, low income workers. and based on how close the transit system is. So the second one is to segregate our data based on the TAZ attributes which affects the transit ridership. So the mode choice of different household also depends on affordability and accessibility. So there are two aspects that is being discussed here: affordability, which relates to the income, and accessibility on how accessible transit system is. To capture the affordability, the TAGs are divided into various groups based on the median income. So the biggest factor that affects the affordability of a mode is median income. So a lot of, let's say, a lot of people from rich, uh, high income background, they can take aviation for most of their travel. But let's say there are some low income background, so they cannot take the aviation mode all the time, so they might take transit mode. So the first factor that affects the mode choice is definitely the median income, and we kind of know that one. And then the car ownership, whether the person or household owns a car or not. So if the household does not have any car or less car than number of people, then there are chances that the household will take the transit system. Now the second one is to capture the accessibility. We use a walk distance to the nearest transit station. So let's say there are some residential area here and the nearest transit station is 5 miles away. Then it's less likely that they are gonna walk or bike 5 miles to take the transit. So usually if it's less than half mile or 1/4 of a mile, then we kind of think that okay, it's within the walkable distance. So depending on how close the transit station is within the TAZ from the households, that kind of is related to accessibility. The second aspect of accessibility or mixed land use of TAZ. This is kind of not intuitive, so let me explain. Let's say um, let's say there is a transit station here. Now a person who usually goes to transit station, let's say a person lives here in their household, usually goes to the transit station if there are mixed land use development around transit station. So let's say there is a grocery shop and there are some other commercial areas, then the person can go to the transit station and do certain other things. So it kind of attracts the transit station more. So that's the importance of mixed land use development near the either the household or the transit stations. Sorry, near the transit stations. So that's how we segment the market. So first we try to figure out what are the network we need to extract for the mode choice. Then we segment the market. And third one is to actually run the mode choice model. In the theory, we looked at multinomial logic regression model. So what multinomial logic model does is it kind of that is the choice is directly related to all the options. However, in practice, nested logic model is used. In nested logic model, first we look at whether driver would choose the auto or transit or non-motorized, and then let's say he chooses the non-motorized, then whether the driver will choose or the person would choose the walk or bike. So this is the nested logic model. It's kind of different from the multinomial logic model, and these are kind of complex equations. So any further discussion on nested logic model is out of scope of this book. We are not going to discuss or even touch it. This is way too theoretical to be a part of this video or book. So just to remember that there is multinomial logic model on which most of the mode choice are taught in school, and in practice uh, nested logic model is typically used. It's just to have that information. But what are these model, how they are built, and there are a lot of mathematics behind it. It's not it's not within the scope of this book to discuss this in detail. We can go for several days just discussing the mathematics behind it. Now the last one is traffic assignment. Traffic assignment, like I mentioned, is my favorite topic in theory. So the knowledge of traffic assignment is regularly needed in practice outside of TDM. So first we look at step one, trip generation. Second, we looked at step two, trip distribution. Third, we looked at step three, mode choice. And now we are looking at step four, traffic assignment. Out of all these four steps, these three are kind of limited to kind of limited to TDM, travel demand model. Mode choice is kind of a part of a bigger choice models where it's used in advertisement and other things. But in general, these discussion of these topics are limited to travel demand modeling itself, whereas traffic assignment is used in other part of traffic operations as well. So traffic assignment is very good concept to know and kind of understand it deeply so that we do a good job at other aspect of traffic operations as well. So traffic assignment kind of helps within the TDM and outside of TDM. So in general traffic ops. In first three steps, trip generation, trip distribution, and mode choice are typically not done outside of travel demand model. However, there are many situations where traffic assignment needs to be performed outside of TDM model. In author's opinion, the knowledge of traffic assignment is most important out of four step of travel demand model, just because it's everything is automated anyway within a travel demand models, but traffic assignment, the knowledge is kind of used to calibrate the travel demand model and also use outside of travel demand model. Traffic assignment is the assignment of OD matrix by each trip purpose onto the transportation network, and for each trip purpose and for each mode selected onto the transportation network to achieve equilibrium flows as we have described in the traffic assignment theory part. So traffic assignment typically consists of two steps. First one is highway assignment. So first, a highway network is created in .NET file format. Like I mentioned, this is called highway skimming. Just a little bit above, we discussed the highway skimming is the same thing. So a highway network is created in .NET file format, and it contains some selected and important attributes. So this is called highway skimming, containing the link attributes that affects the travel time and cost. Some attributes that affect travel times are free flow travel time, link capacity, alpha and beta value of BPR function. Travel cost is typically Travel cost typically involve operating cost and toll cost if applicable. So so the highway assignment is based on travel time plus travel cost, which is converted into generalized cost. So travel time is a function of all the attributes in the BPR function, and travel cost is a function of operating cost, which depends on distance, and toll cost if applicable. Different networks are created for AM peak because the travel time and link flows are different. So different networks are created for AM, midday, and PM and nighttime period. Multinomial, okay, this is an important statement, so I'm going to use a different color here. This in itself has a lot of information, so this is an important one. Multinomial multi-class assignment is performed using biconjugate Frank-Wolf algorithm, Frank-Wolf user equilibrium. So this has two information. First, what is multimodal multi-class assignment, MMA? So multimodal by definition means it involves different kind of options. It use transit, it can use uh, transit, private cars, and if other bike, aviation, and then multi-class. So what multi-class means is usually we have different OD matrices for different class of vehicles. So let's say the first OD matrix is for car. The second OD matrix is for small trucks. Next OD matrix is for shared vehicles. The next OD matrix is for bigger trucks. This is what is meant by multi-class assignment. In multi-class assignment, we are looking at different classes of vehicles, and for each of these vehicles, there are different OD pairs. So multimodal, multi-class assignment. Compared to this, there is a single class assignment, which combines all the ODs to run uh, just a single OD assignment. Is performed using biconjugate Frank-Wolf algorithm. So we already talked about the biconjugate Frank-Wolf user equilibrium in the theory. So just to mention here that in most of the cases we use biconjugate Frank-Wolf user equilibrium, which is based on the property that user equilibrium is a convex optimization problem. So user equilibrium optimization problem is convex, and biconjugate Frank-Wolf algorithm is an advantage over regular Frank-Wolf algorithm because it converges faster. So just some terms to remember, nothing to just some terms to remember. So we usually have to do traffic assignment several times by ourselves within Transcat. So we need to be familiar with these terms so we can use them when we are manually assigning, uh, when we are manually doing the travel demand modeling calculations. Transit assignment uses a pathfinder assignment techniques that finds the best transit paths using generalized cost that considers travel time, fare, number of transfer, and other factors. I don't need to explain anything more on this. Feedback loop. Now we notice that trip generation. First, all four steps of travel demand model are connected to each other. So for example, first one was trip generation. So let's say we have a centroid here and a lot of vehicles are coming out. But if the number of vehicles from a centroid exceeds certain capacity of the link, then not all the volumes are loaded on the network. So there are some, let's say the total volume generated is 5,000. And out of 5,000, let's say 3,000 vehicles got loaded, other got stuck at the node or initially at here itself. So there is something called latent demand. So 2,000 vehicle will be considered as latent demand. And if we improve the roadway system, this additional 2,000 vehicles will be added on and distributed. So depending on how roadway is doing, the trip generation is affected. Trip distribution is also directly affected by the travel time on the links. So like we talked about, so the in the trip distribution stage, let's say this is my origin and this is destination number 1, destination number 2, destination number 3. There are 3 different destinations. So the number of trips that are assigned to different destinations depends on the impedance factor, and impedance factor depends on the travel time. So overall, the trip distribution depends on, we can say, travel time that is assigned to the network. So in the traffic assignment stage, the output is link flow and link travel time. So the output of traffic assignment is link flow and link travel time. Now trip generation itself depends on the link flow and link travel time. Trip distribution depends on the link travel time. Mode choice is also dependent on the link travel time. So let's say there is one route which has travel time of 100 minutes, and and the car can go through this one, or there is a public transit that can go through this route and it is only let's say 5 minutes comparatively. Then the user may choose the transit because it's relatively much faster than using the car. But let's say this instead of 100 minutes, this road is 1 minute, and then the person may consider driving their own vehicles because now this is much faster than transit. So the mode choice in itself depends on the travel time by different modes, which in fact depends on the traffic assignment. So all in all the four step trip generation, trip distribution, mode choice, and traffic assignment. They are all connected to each other. So when the traffic assignment step is done, the travel time is updated. Once the travel time is updated, all of the steps needs to be updated. So this travel time data is fed back into trip generation runs again, then which is fed to trip distribution until a convergence is reached. So this is called feedback loop. Feedback loop is very important in TDM, uh, because the time it takes to run one feedback loop. So hence here it should be noted that running one iteration of TDM takes about 3 to 8 hours, just one iteration. So maximum number of iterations are typically limited to 15 iterations. So if one iteration is taking 3 to 8 hours, then we can imagine if we are running typically the travel demand models run between somewhere between 8 to 15 iterations. So on an average, it takes about 6 hours. So if a travel demand model for one feedback loop is taking 6 hours, and let's say on an average number of iterations are 12, then we can calculate how many days it will take to run the entire model. So 72 hours, which is equal to 3 days. 3 days is a typical value. 3 days is a typical number of days that travel demand model runs full run. So is feedback loop is kind of important, depending on where we are setting the convergence. The uh, model keeps running in a loop. So that's all there is on the implementation side of travel demand model. This is how travel four-step travel demand model is coded within the TDM. We looked at how trip generation is coded. In trip generation, we looked at the census data, how census data is transferred into TAGs, and using the distribution curves, those TAG attributes are then split into different categories, and those categories are then applied onto cross classification regression equations to calculate total number of trips. After getting total number of trips, there is trip balancing. uh, Trip balancing is done based on trip purpose, figuring out whether the production is more reliable or attraction is more reliable. In trip balancing, if we are looking at home based work trip, then the production is more reliable. If we are looking at home based non work trip or any other besides home based work trip, then usually attraction is more reliable. So depending on which one is more reliable, we balance the other one. Then we looked at the trip distribution, which is done based on standard gravity model, and this is a step where we are trying to come up with various parameters such that the output of trip distribution matches the field OD matrix. So the output of trip distribution is a OD matrix, and we are trying to adjust the parameters or calibrate the parameters such that the output of trip generation is matching the field collected OD matrix. This is typically done while the model is being developed. This calibration is not a part of calibration we do while working on project. This is a calibration that is done while developing the model itself. Then we looked at the mode choice using mode choice is done using nested logic model, and not much discussion is needed on this. Then last one is traffic assignment, which is very important. Traffic assignment is done using multi-model, multi-class assignment, and using biconjugate Frank-Wolf algorithm for faster convergence. Then towards the end, we discuss the feedback loop. So how all the steps are connected to each other. Step 1 goes to step 2 goes to step 3 goes to step 4. Now step 4 is already connected to all other steps. So now once the step 4 gives an output, all other steps must get updated. So that creates a feedback loop. However, given the big data set we have in travel demand model, one iteration of all 4 steps typically take around let's say 3 to 8 hours, on an average 6 hours. Even with a very fast computer, on an average it takes around 6 hours. And it typically converts between 8 to 15 iterations. So a travel demand model typically runs for 3 days, and if we have not set up the model correctly, then 3 days of our run goes to waste, and then we have to change certain things, and then we have to run it again. And in order to know the results, we have to kind of wait for 3 days. Or what we can do is we can run the intermediate steps, trying to figure out whether the final output will be correct or not. However, working with TDM is kind of a tedious process, just because the amount of time it takes to run one entire feedback loop to come with a converged linked output. So at the end, we get the link flows and link travel time. So at the end, what we are looking for is link flow, link flow, and link travel time. That's all we are looking for. Sometimes we are also looking for OD metrics, final OD metrics that is assigned. And these are the output we look from the travel demand model. So in the next video, we will talk about how to use this travel demand model. So in the first part, we looked at theory, then we looked at how the model is set up, then we looked at, after setting up the model, how the four-step travel demand model is coded inside the TDM model, and next we will look at how to use the model. So by here I use means, let's say we go and get the travel demand model from state agencies, then what should we do with that model? So everything so far has what has been discussed is while developing the model itself, the knowledge we need to kind of develop the model itself. And next we are uh, going to kind of go through how to use that model. Now once we have built this model, how to use it. In order to understand how to use that model, we also need some background on how that model was built in first place. That's why we went through so many videos discussing how these models are built, and in future videos when we are discussing how to use these models, then some of the concepts will come back. So I will see everyone in the next video to discuss, once we receive this model from agencies, how to use them. Thank you for listening in, and please watch out for the next video.